Before I started recording this, I forgot to finish off this question here, but it's okay. We'll go ahead and record this video. What we're going to do is we're going to apply these three transformations, and it's going to be applying transformations in concession and in orders. So we have number one, number two, number three. We have dilation, reflection, and translation all applied to the same equation. I'm just trying to figure out what equation to use, and I will probably use the square root graph, y is equal to the square root of x. Apply our transformations towards here. Sweet. So there's two main things I want you to take away from this video. The first one is the order of the transformations matter. So you can see that we have three transformations here. So we have dilations, reflection, and then translation. And what we're going to do in the second half of this video is apply the same transformations, but we're just going to do it in the reverse order. And we're going to see how the image equation of our square root graph looks slightly different after we do it in a different order. The second thing I want to see is just how we actually apply multiple transformations at once, because we haven't actually done that before. We've only found x dash and y dash expressions after one transformation. So how do we actually apply it when we have multiple transformations in succession? I think I said concession before, but I meant to say succession. So let's take y is equal to the square root of x, and we're going to apply these transformations in order. Now, we're going to do the long way, but as I said before, once we know the long way and we kind of understand how it works, then we can use the shorthand way, which is on the last column of that table, which is in the description. So the first thing we're going to do is apply the dilation, and then the reflection, and then the translation. So what we do is we start off with x dashed and y dashed. Now this is actually how I like to apply transformations in concession. I do it in coordinate format just to make it a bit easier to note down, and it also is slightly more organized when you have multiple transformations. So we start off with x comma y, and then what we do is we essentially we're finding our x dash and y dash expressions at every step. So the first one is a dilation by a factor of 2 from the y-axis. So what that's going to be is just multiplying our x value by 2. So we're going to replace x with 2x, comma y. Now what we do is we just apply the transformation that's next in order to our previously found x dash and y dash at this step. So we can see we have a reflection in the x-axis, and we know that that makes the y value negative. So what we're going to do is still keep 2x, but then we just make it negative y. And then for our last step, what we're going to do is a translation of 4 units in the positive x direction. Now this is where just doing things in order is really important, because a translation of 4 units in the positive x direction just adds 4 to this full expression here. It doesn't add 4 just to the x value, it adds it to this whole thing in this x slot, if that makes sense. So what we're going to do is do translation of 4 units in the positive x direction, makes this become 2x plus 4, comma, negative y. And that's why applying the transformation step by step is really important, because a lot of people, they might write 2 outside of x plus 4 in with a bracket. But what we need to do is, because we've done the dilation first and then the translation, we need to evaluate this 2x and then plus 4 on the outside of that full expression. So what we can say now is that, maybe I'll use a different color for this step. What we can say now is that x dashed is going to equal this final expression that we found after all of our transformations were applied. So x dash would be equal to 2x plus 4, and then y dashed is simply equal to negative y. And then we go through our usual process. We rearrange for x, and we rearrange for the regular y as well. So if we rearrange for the regular x, what we get is x is equal to x dashed minus 4 all divided by 2. And then y is pretty simple. Y is equal to negative y dashed. And then we substitute these equations into y is equal to the square root of x. So we take y is equal to the square root of x, and that becomes negative y dashed is equal to the square root of x dashed minus 4 divided by 2. I guess we can write it like that, or you can take out the 1/2 on the outside. I might do that for the last step. So then we get y dash is equal to negative square root of 1/2 x dash minus 4. I just mean it like that. That would be how I prefer to represent it, but honestly, both of them are algebraically the same, so you can represent it as either way. Therefore, image equation is y is equal to the square root of 1/2 x minus 4. Sweet. Now, sorry, I've got a negative there. Cool. Now, what I would say is to look at this equation and see how these transformations are reflected on there or represented on there. So what you can see is that each of our parts of our equation, it pretty much corresponds to one of our transformations. I'll give you an example. This negative here, we know responds to or reflects to the reflection in the x-axis. This 1/2 here is a representation of the dilation by a factor of 2 from the y-axis, and then the x minus 4 is a representation of the translation of 4 units in the positive x direction. So when you look at each of those values or each of these components of our transformed equation or our image equation, you can see that each of them are represented pretty clearly. Now, this might not always be the case. There's sometimes where transformations might merge together. For example, sometimes if you have a dilation in the x-axis and the y-axis, sometimes they're forced together. And I'm going to produce another example at the end of this video, or maybe at the start of the next video, which shows that sometimes if you have kind of clashing transformations, then they can influence how the graph is actually represented. And sometimes you can get transformations that are represented identically. So for example, there might be an equivalent set of transformations that is different to this list here, but it produces the same result. And I might have complicated that by saying that now, but just note that this set of transformation is not exclusive to just this equation here. This equation here can be produced by multiple sets of transformations. This is just one of them. So there are equivalent transformations that we can use, but we'll go through that potentially in the next video, but I'll make it clear in the next, in the description also. So now this is the equation of our image after applying these transformations here. I'm going to go ahead and rub all this out, and then we are going to do the same transformation set. We're just going to do it in the opposite order.